Welcome back, everyone. We've reached the 9th episode of this course on computer vision systems. Today, we'll look at an example of how to define a vision system, starting from an object and outlining all the components we need in order to measure it. Before we start with the example application, let's see how everything we've discussed about lenses and cameras ties into vision systems. The diagram you see here, which we've already described when we talked about optical system geometry, shows how a point in the object plane is focused onto the image plane. Now let's try removing one of the two light rays, and also try rotating the entire figure. What you get is the actual simplified diagram of a vision system, where at the bottom, so in the same object plane as before, we find the field of view. That is, the plane where the object to be captured is placed. At the top, instead, is the plane where the image of the captured object is formed. This plane coincides exactly with the camera sensor. At the top, we find the camera and optical system, while at the bottom, we find the object to be measured. Whereas before, we talked about the image plane, lens aperture, and object plane, now we'll talk about the camera sensor, optical system, and the object being measured. And what are the laws that govern the system? We already know one of them is the relationship that connects them. Object distance, image distance, and focal length. In this case, we call the object distance the working distance, or WD. From this formula, we see that if the working distance is much greater than the image distance, the focal length is exactly equal to the image distance. This means that if the object is very far away compared to the space between the lens and the sensor, which is almost always the case, then the image, it'll form exactly at a distance equal to the focal length. The second formula that governs vision systems, on the other hand, comes from geometric considerations related to the similar triangles formed in the diagram. In particular, the following proportion is true. The sensor size, or SS, relates to the focal distance, f, just as the field of view relates to the working distance. This proportion allows us to determine any parameter, as long as the other three are known. Now that we have all the necessary equations, let's look at a practical example of how to design a vision system. Let's suppose we need to measure this object, an O-ring with a nominal diameter of 60 millimeters. The questions we need to ask ourselves are, which camera should I use? Where should I position the camera? Where should I place the object? And what kind of lighting do I need? There are several ways to answer these questions. Let's start, for example, by defining the field of view. Let's assume that the O-ring needs to be fully visible within the image. And let's also suppose we have a certain margin of positioning error, for example, 10 millimeters on each side. At this point, the field of view will be 60 plus 10 plus 10, so 80 millimeters. Now that I know the FOV, let's set, for example, the spatial resolution of the image. So let's set how many millimeters of the object plane are covered by each pixel of the sensor. Let's assume we have a spatial resolution, RS, equal to 0.1 millimeters per pixel. This means that each pixel of the camera will cover 0.1 millimeters on the object plane. Knowing the FOV and the spatial resolution, we can determine the minimum number of pixels the camera must have, that is, its image resolution Ri, simply by dividing the FOV by the RS. In this case, the Ri comes out to 800 pixels. This means that if I want a field of view of 80 millimeters with a spatial resolution of 0.1 millimeters, I'll have to choose a camera with at least 800 pixels. Now that I know the minimum resolution of the camera, I can choose the most suitable model from the various manufacturers. Once I've chosen the model, I note down the most important parameters, which are sensor size and pixel size. At this point, we only have the last two parameters left to choose. The focal length, and therefore the lens to mount on the camera we just selected, and the working distance, which is the distance at which I'll need to place the object to get the desired field of view. To do this, we can use the proportion we saw earlier. Sensor size is to focal length as field of view is to working distance. In this case, We know the sensor size and field of view, while the focal length and working distance are unknowns. To solve the problem, I definitely need to define one and then calculate the other accordingly. To do this, I need to keep in mind that the greater the focal length, the greater the object distance. This leads to bulkier systems. The shorter the focal length, the shorter the object distance, and this results in systems that are more affected by optical aberrations, even though they are more compact. Keep in mind that I'll also need to consider the depth of field, which, as we've seen, is related both to the focal length and to the distance of the object to be measured. By doing this, we've traced back all the parameters that govern our vision system. Field of view, spatial resolution. Camera, focal length, and working distance. However, keep in mind that this is just one of the possible approaches. In fact, depending on the specific application, I could follow other solutions. Obviously, to do this, you need to know the equations that govern all these parameters. At this point, you'll need to choose some of them and, of course, determine the others using these very equations. Finally, let's define the illuminator. Since I need to measure a diameter and not, for example, read an inscription engraved on the ring, it's perfectly fine to use a backlight type illuminator, which allows us to see the edges of the object very clearly. And to make sure that these are highly contrasted against the background on which the object is placed. With this example, we've seen how it's actually possible to derive all the parameters that allow us to build a real vision system. At this point, we can move on to the last remaining block, the software part. The software will allow us to obtain the actual final measurement.